Hello, and thanks for your continued interest in the subject of shaft alignment. This tutorial will discuss what is needed to obtain accurate alignment measurements and a way to verify that your readings make sense using a mathematical principle called the Validity Rule. This information will hopefully assist anyone who is responsible for installing or maintaining rotating machinery such as motors, turbines, pumps, fans, gears, compressors, and generators, for people who evaluate the operational or mechanical performance of machinery, and for technicians and engineers who are responsible for rotating equipment. So, this information is intended for trades personnel, maintenance supervisors, training instructors, mechanical procedure writers, vibration analysts, engineers, maintenance managers, and any interested operations personnel. When aligning rotating machinery, it is imperative that you obtain accurate shaft positional measurements. It is very easy and very common to make mistakes when taking these measurements, so this tutorial will illustrate what you have to be aware of when taking your alignment readings to ensure that the measurements you obtain are accurate and repeatable. There is a mathematical pattern that occurs when taking readings at 90-degree intervals around the shaft. This pattern is called the Validity Rule. The Validity Rule will confirm that your measurements make sense, but more importantly, can derive a missing measurement if you cannot rotate all the way around the shaft. When you are ready to take a set of alignment measurements on a shaft, a dial indicator is typically placed in a 12 o'clock position on the shaft or coupling hub. The stem of the indicator is plunged in about halfway in its total stem travel, and the number dial is set to read 0. If there is a slight amount of runout in the shaft you are taking a reading on, then it is a good idea to put a scribe mark with a pencil or a marker on the outer surface of the coupling hub at 12 o'clock to use as an angular reference point. If you have already done a runout check, you may already have a mark where the high spot or low spot is, so you could use one of those as your angular reference position. In this case, we are using the keyway as an angular reference position. When you are ready, slowly begin to rotate the bracket and indicator so that you can observe whether the needle is sweeping in a clockwise or a counterclockwise direction. Here, in this particular instance, we notice that the needle has rotated in a counterclockwise direction. Again, this means that the stem of the indicator is moving outward to maintain contact with the surface of the coupling hub. By convention, that is a negative reading, so right now the indicator is reading a -10. Continue rotation, watching what happens to the needle on the indicator. At this point, the needle is still rotating in a counterclockwise direction and is now at a -40. If the coupling has been disengaged, and you know that you have a couple of mils of runout to contend with, there is nothing wrong with rotating the shaft with the bracket and indicator attached to it first, then rotate the shaft that the indicator is taking a reading on until your reference mark catches up with the stem of the indicator. As rotation continues, the needle continues to rotate counterclockwise and is now at a -55, and again, you can rotate the shaft to catch up with the indicator position. We've now rotated the bracket and indicator through a 90-degree arc, but before you record this reading, rotate the shaft so your reference mark catches back up with the stem of the indicator. Okay, on that side we have a reading of a -78, so now is a good time to write that down on your alignment recording sheet. Here is where the classic mistake of writing down a reading on the wrong side of the recording sheet occurs. Which side is the indicator currently at? Is it on the south side or on the north side? This may seem trivial now, but this is a fatal error if you get this wrong. Again, slowly continue rotating the shaft, observing the needle on the indicator. At this point, the indicator is now reading minus 103. This is another major point of confusion when reading dial indicators. Yes, I know the needle looked like it went back to 0 and is now reading minus 3, but it actually swept completely around to a minus 103 mils. As rotation continues, the needle continues sweeping to minus 112. And as rotation further continues, we notice that the needle has stopped sweeping and is stuck at minus 112. But also notice that the stem of the indicator is no longer touching the coupling hub. This is something that you have to watch for. The stem of the indicator must touch the surface of the shaft or coupling hub all the way around when you are taking your readings. The same is true if the needle is rotating clockwise. If we start back up at the 12 o'clock position and rotate the other way, notice that as rotation starts, the needle now sweeps in the clockwise direction to a plus 35, then to a plus 62, and as rotation continues, well, the needle stops sweeping and we have bottomed the stem out to the point where it can't get pushed in anymore. Bottoming an indicator out when sweeping positive measurements, or the stem coming off the surface when sweeping negative measurements, is somewhat common, so you need to watch for both of these issues when taking your readings. No matter what kind of alignment measurement system you are using, it is a good idea to take at least 2 sets of measurements. Here we have a bracket and dial indicator positioned at 12 o'clock, with the stem of the indicator plunged in about halfway and a needle pointing at 0. On our measurement recording sheet, we've drawn a circle and labeled the 4 clock positions at the top, bottom, and in this case, we happen to be working on a drive system where we are facing south as we are viewing the shafts. We rotate the shaft through a 90-degree turn, watching the indicator as we rotate, so we can observe if the needle is sweeping in a positive or negative direction. When we get over to the north side of the coupling hub, we notice that our reading is a minus 6, and judiciously write down the minus 6 reading on the north side of our reading circle. We then rotate the shaft through another 90-degree rotation and notice that the needle rotates back to 0, then continues a clockwise rotation to a plus 42 when we arrive at the bottom. This is another common occurrence when rotating around the shaft. The dial indicator may begin to sweep in one direction, stop, then begin sweeping in the other direction as it traverses through a 90-degree arc. Again, we write down the bottom reading on our reading circle. Again, we rotate another 90 degrees so the dial indicator is now on the south side of the coupling hub. We note that the reading on the south side is a plus 49, and we write that down on our reading circle. We rotate back to the top and notice that the dial indicator is reading a plus 1. Close, but not quite back to 0. This is very common. Due to some hysteresis in the indicator and that we didn't rotate exactly 90 degrees each time, the return measurements may be slightly different, so let's re-zero the indicator at the top and repeat the readings again. The second rotation to the north side yields a -8. The next rotation to the bottom yields a +44. The next rotation to the south side yields a +51. And a return back to the top yields a -1/2. If we continue sweeping around and around several times, the average reading on the north side is a -7. The average reading on the bottom is a +43. And the average reading on the south side is +50. Also notice that each set of readings is adhering to the validity rule. Huh? The validity rule? What's that? There is a mathematical pattern that exists between the four measurements we obtain at each quarter turn. The pattern is referred to as the validity rule. In other words, are the measurements we obtained valid measurements? Typically, we set an indicator at the 12 o'clock position on a horizontally oriented shaft, plunge the stem in about half of its total travel, and zero the indicator. Why do we do that? Well, we zero it there for convenience because it's usually easy to see the indicator when it's positioned on top of the shaft. We plunge the stem of the indicator in halfway because when we rotate the bracket and indicator around the shaft, we do not know if the indicator stem is going to get pushed in or if the indicator stem has to move out to main contact as we sweep around the circumference of the shaft or coupling hub, or if both will happen through the entire rotation. If we zero the indicator on the top side, the validity rule states that when you add the two side readings together, it should equal the reading on the bottom. Another way of saying this is that the sum of the measurements on the top and the bottom should be equal to the sum of the measurements on the sides. And yet another way of saying this is that when you add the two readings that straddle the zero together, they should be equal to the reading that is opposite of the zero. The validity rule should work to plus or minus 10% of the largest number in the reading set. Let's take a minute and run through a few examples. But before we do, why is the validity rule important? Well, for one reason, we want to make sure we are getting good readings because the success of the alignment corrections is directly related to the accuracy and validity of these measurements. The other reason, and one that has helped me several times, is you don't have to rotate all the way around the shaft to get a set of alignment readings. You only have to rotate halfway around. Sometimes when you are trying to measure the alignment, you can place the indicator on the top and you can rotate over to one side, but then when you try to rotate down to the bottom, something gets in the way, like a lube oil pipe or the base plate. Well, that's not a problem. Just rotate over to the other side, and with the top reading and the two side readings, you can figure out what you would have got on the bottom without ever having to get there. Here, in the first example, the indicator was zeroed on top, and the readings on the east and west sides have been measured. If we could have got to the bottom, what would we have got? A plus 55. That's correct. A plus 40 added to a plus 15 is a plus 55. Okay, here's another one. We have a minus 63 on the east and a minus 27 on the west. What should we get on the bottom? Right, a minus 90. Minus 63 plus a minus 27 equals a minus 90. Next, we have a minus 48 on the north and a plus 29 on the south. What should we get on the bottom? A minus 19. Yeah, that one was a little tougher. This is about as difficult as the math gets in shaft alignment. Indeed, there is geometry and trigonometry involved in determining the corrective moves, but there is a way to do this without complicated math. As you saw in the tutorial on alignment tolerances, you can take these measurements and construct an exaggerated yet accurately scaled picture of your misalignment condition that can help you figure out what to do. These accurately scaled pictures of your misalignment condition are called alignment models, and there are some very powerful things you can do with them. But what's really neat is that all of the geometry and trigonometry involved to determine the corrective moves just naturally happens in the alignment models without having to plug numbers into any complicated equations. But you are going to have to know how to add positive and negative numbers together. You're going to have to know how to divide a number by 2, and you're going to have to know how to count squares on a grid. Let's do a couple of more example problems that will hopefully fine-tune your math skills on the validity rule. Here, we've zeroed an indicator on the top, observed a plus 29 on the south side, and a minus 48 on the bottom. What should we get on the north side? Remember, the two numbers that are straddling the zero, when you add those two numbers together, they should be equal to the number that is opposite of the zero. The two numbers that are straddling the zero are the north and south numbers. Well, we don't know what the north number is, but we know this. The north number added to the south number should be equal to the bottom number, right? So on the north side, we should get a minus 77. Well, you're on vacation, taking a cruise in the Caribbean, and all of a sudden the ship stops. The captain gets on the loudspeaker and asks if anyone is an expert on rotating machinery because they are having some problems with the alignment on the propulsion drive, and if anyone can help, they will be awarding an all-expenses-paid lifetime pass for any cruises for the person, along with 10 family members or friends who can fix their problem. You look around, and everyone in the ship are staring out into space with a befuddled look on their face, and it dawns on you that you can do this. So you go below deck into the engine room, and there is the chief engineer, the maintenance manager, and 4 mechanics who are trying to perform the shaft decoupling spool method with a bracket attached to the crankshaft of the diesel engine and a dial indicator taking measurements on a drive shaft, but they could only get 3 readings because the coupling guard is on the way on the starboard side of the drive shaft, and they don't know the validity rule. But you do. After pondering the readings they got on the port and hull sides, you think for a minute and tell them that the reading on the starboard side of the drive shaft is going to be plus 36. Hooray! Okay, now wake up from your dream. Anyway, who says we have to zero on top? In this example, for some reason, you can't get on top. This actually happened to me once working on a test drive system where there was a disc brake assembly in the way of putting an indicator on the top of a shaft. So I just rotated the bracket and indicator over to the east side and zeroed it there. Then I rotated down to the bottom and got a plus 50. Then I rotated over to the west side and got a minus 24, and that's all I needed. Now, if I could have got up top, what would I have got? Remember, the two numbers that are straddling the zero should add together to equal the number that's opposite of the zero. The two numbers that are straddling the zero are the top and bottom numbers. Well, we don't know what the top number is, but we know this. The top number added to the bottom number should be equal to the west number, right? So on the top, we would have got a minus 74. Let's take a closer look at that last example. What you need to understand is that the individual numbers by themselves don't really mean anything when aligning rotating machinery. What's important is what happened from the top to the bottom and what happened from the east side to the west side. Someone might ask, if you could have zeroed the indicator on the top and swept all the way around, what would you have got on the east, bottom, and west sides? Well, we can figure that out. The top reading is a minus 74. What do we have to do to that number to make it go to zero? We have to add a plus 74 to it. Minus 74 plus 74 equals 0, right? If we add 74 to the top number, add plus 74 to every other number in the number set. On the west side, minus 24 plus 74 equals plus 50. On the bottom, plus 50 plus 74 equals plus 124. On the east side, 0 plus 74 equals plus 74. The reading set on the left and the reading set on the right are telling us exactly the same thing. From the top to the bottom, the stem of the indicator got pushed in 124 mils. From the east side to the west side, the stem of the indicator moved outward 24 mils. What change occurred from the top to the bottom, and what change occurred from the east side to the west side? That's what's important. As mentioned a few slides back, the validity rule can deviate up to 10% of the highest number in the reading set. Why doesn't the validity rule work perfectly every time? Well, there are a couple of reasons. Probably the number one reason is that you are not making precise 90-degree rotations when you get your readings. When you set an indicator at the top of a shaft, it is fairly easy to see where the stem should be in the 12 o'clock position. When you rotate 90 degrees over to one side, it might look like you're on the side of the shaft or coupling hub, but you might have stopped a little bit short. Then, when you rotate to the bottom, you might overshoot a little bit. On your rotation over to the other side, well, you didn't quite make it there. This is probably the major reason why the validity rule deviates. If you disengage the coupling and have some room between the shafts, you could, for example, use a plumb bob to mark off the top and bottom positions, then use a carpenter square to mark off the two side reading points. Or you could use a 4-point alignment level bubble. There are two spirit levels placed 90 degrees apart, and there is a magnet on the back side of the device. After you position your indicator at 12 o'clock, level one of the two bubbles. Then, to know that you rotated 90 degrees, the other bubble comes in. Also notice that the indicator is actually touching another bracket attached to the other shaft. You don't have to position the indicator directly on the other shaft or the surface of a coupling hub. Assuming that you rotate both shafts together, you could use another fixture attached to the shaft you are measuring as a platform for the indicator stem. The indicator thinks it's just positioned on a larger diameter coupling hub. Another reason the validity rule may deviate is that the indicator is not perpendicular to the tangent of the curved surface you are measuring. Now, if the indicator is off by 10 degrees or less, then it's probably not going to have a big effect. But if the indicator is off perpendicular by 30 degrees or more, it is probably going to have an effect on the accuracy of the measurements. Another reason the validity rule may not add up perfectly each time is that if there is an acute angular misalignment involved, the indicator traverses an elliptical path, not a circular one, and now you are comparing the distances of the major and minor axes of an ellipse. It doesn't matter what alignment measurement system you choose to use. You can use one that you made for $100 or one that cost as much as a new car. But I strongly suggest that you take at least 2 sets of measurements before you do some movement calculations, or worse yet, make the wrong move based on bad measurements. The more precise your angular sweeps are, the more accurate your readings will be. Try to rotate as close to 90 degrees each time you take a set of measurements. The validity rule helps ensure that you are getting good measurements, and it can be a lifesaver if you can't rotate all the way around a shaft.